Hello, I'm Mikhail Kamalov. I'm a PhD student in Philosophy and Antipolis, and Konstantin Overchikov, my scientific advisor. Let me present my ongoing research in topic of genetic modeling and supervised learning. Also, I want to mention that this work supported by my data models company. So, first of all, I want to show my overview of my talk and begin from very brief explanation of variational autoencoder. The variational autoencoder is a model which allows to reduce dimension of observed object X into dimension of latent object Z. This model based on very simple assumptions that our X generated from latent space Z and this Z generated from normal distribution. Based on these two assumptions, we can apply divergence between synthetic Z generated by neural network. Here you can see that we use a layer for expectation and layer for variance, which use a reparameterization trick to generating synthetic latent Z by neural network. And we also take into account as like Z from our assumptions that are generated from normal distribution, and based on synthetic and like real latent Z, we can minimize the distance and try to improve our representation of X in latent space. And the second minimization function, it's a simple function which try to minimize loss between recover input and real input. So now let me also briefly present the works which we take into account during developing of our algorithm. The first work is PageRank semi-supervised learning based on this minimization functional. This functional contains of two parts. It's Laplacian regularization loss and standard supervised classification loss. And this work present the explicit solution of this functional and algorithm which allows you avoid the invertencing of higher matrices, and at the same time goes to explicit solution of this functional. The second algorithm, this is a variational semi-supervised learning model, which based on modification of variational autoencoder. And here you can see that we take into account information of our labels of nodes during recovering our X, and also we take the label information during generating of our Z. So now I want to define the main issues of these two algorithms. And for PageRank, this is the main problem with dimensionality reduction, because in case if we doesn't have real adjacency metrics, we can try to compute the distance between our objects, but if our dimensionality goes to infinity, we can get the average distance between, the same distance between our nodes. The problem in variational semi-supervised learning is that this model doesn't take into account adjacency metrics and graph structure at all. And the general problem of these two algorithms is that in case of binary adjacency metric structure, we lost information about how the nodes really connected, the real similarity between papers. So in order to resolve the aforementioned problem, we decided to take the best part from variational autoencoder and PageRank algorithm and combine these two best parts into our generative PageRank algorithm. Here is the functional which we want to minimize in our generative PageRank algorithm, and these parts this functional consists from two parts. The part with variation of the encoder, which includes information from generative PageRank layer and the output from multi-layer perceptron. As well, we try to take into account the categorical cross-entropy loss, which minimize distance between real labels and output from PageRank. So how it looks like in terms of architecture and layer structure of GAN-PR algorithm. At the beginning, we put our information about nodes into multi-layer perceptron, and this prediction we use into expectation part of variation of the encoder. And in parallel, we train the variational layer for further computing the representation trick for our latent representation of object. And here is the main part, an important part of our algorithm, which based on computation the distance between expectation of objects in latent space, which already includes information about classes, like through the multi-layer perceptron. And it includes information from the latent space as well, which allows us to get more closest and more useful information about similarity of nodes. And based on this information, we're weighting our default adjacency matrix. Then we normalize this matrix and use it for PageRank iterations to better clarification of predictions from multi-layer perceptron. Then we use this output from PageRank to recovering our real X from latent space Z. Here I present the two variants of generative PageRank. First part is inductive generative PageRank, which consists and see like two parts with parallel training. Parallel training means in parallel you train variation of the encoder with output from multi-layer perceptron, and also you modify it and recover. This is part of decoder, right? This is part of encoder, and you encoder and decoder part take into account the output from classifier PageRank and MLP. In case of transductive learning, you just focuses on separate training, like before you train your variation of the encoder, then you train your classification part and take the output from variation of the encoder to regularize adjacency metrics for improving the classification of nodes. Then let me show our experimental results. Here is the comparison on 4 data sets. And here you can see that GNPR outperformed all the state-of-the-art models. And also we show that we significantly outperform APPNP because APPNP also apply a generative PageRank algorithm for classification, but it based on default adjacency metrics. And we wanted to be sure that reweighting of adjacency metrics can really impact on quality of classification. And here you can see that based on t-test, we can show that we can outperform this algorithm. Also, we show that for number of iterations, we have to use less number of iterations than APPNP to get a better classification results, which allows us to reduce the number of computational time. And finally, I want to show that our algorithm can also be useful in terms of explication of your results, result of classification. This is default graph. This is graph with related edges by variation of the encoder. And this is, we try to explain why we have this kind of label on this node based on similarity in latent space and already labeled neighbor nodes. So this can be used as possible part of explanation result of classification. So that's it from my side. Thank you for your attention. Questions?